This is a vector for AQA Further Pure Mathematics, Vectors section 1.1, where we're looking at using vectors. At GCSE you will have been introduced to vectors in 2 dimensions. So remember that when we write vectors they can be written as AB, for example that's the start and the end point with a line over the top, or just given a name, for example A underlined. In bold print in text rather than underlining is quite common. In 2 dimensions we can give it in vector form, component form, so that vector A would have 2 parts to its column vector, A1 and A2, so A1 in the X direction and A2 in the Y direction. As I've already said, if we have printed text then it's probably going to be in bold, but you should always underline when you're writing. Vectors can be added, subtracted or multiplied by a scalar. So here we've got 2 vectors, A which is 4, -1 and B which is 1, 2. So if I wanted to add those together, then clearly we're going to get the 2 column vectors added together. So we have 4, -1 and +1, 2, which gives us a value of 5, 1. Now if we indicate on the diagram, if I mark in a vector which is equal to B at the arrow end of A, then this is equivalent to B, and A plus B is given by the vector which goes from the start to the end, and you can see that is 5, 1. If we want A minus B on the other hand, then we have 4, -1, and we have to think about it as being plus the negative of B, but I can write it as just minus 1, 2, and we end up with 3 and then -3. But on the diagram, let's say we have to do it as A plus -B. So -B is a vector down in this direction, so in the opposite direction to B, and if I put that there joining on to the arrow end of A, then my result is this vector here, and that is A minus B, and again you can see that that is 3 along and 3 down, so 3, -3. And finally multiplying by a scalar, so if I want a vector which is equivalent to 2b, that would be equal to 2 multiplied by 1, 2, so 2, 4, and on the diagram it's just a case of adding in another value of b, or another vector equivalent to b on the in here, so this b is added on, so we get 2b is equivalent to b plus b. So the vector from the start to the end there, let's just put it in a different color. The vector from start to end here is equal to 2b. Now I've got this all shown on a rather neater diagram on the next slide. The length of a vector is known as its magnitude or modulus, and the symbol for that is to use 2 straight lines around the vector, so mod A or mod of AB. And we can find that by using Pythagoras' theorem. So Pythagoras' theorem, of course, tells us that the length of A will be equal to the square root of A1 squared plus A2 squared. So on the diagram then we've got the 2 lengths here, A1 in the X direction, A2 in the Y direction, and it's a right angle triangle, so Pythagoras' theorem is used. Sometimes we write vectors in terms of what are called the unit vectors I and j. So the unit vectors are vectors which are length 1, in the direction of the x-axis and the y-axis. So the vector A here is written as A1I plus A2J. So A1 and A2 are then just the multiples of I and J. So if we have a vector, we can then talk about, well, what is the length of, or what is the vector which is length 1 unit in its direction. So if this is vector A, then we can consider what is the vector of length 1 in the direction of A. And this we refer to as A hat. So unit vector in a particular direction, A hat. And we can find that by taking the vector A and dividing it by its length. So A hat is A over the modulus of A. So in an example of that, here we have a calculation for the vector 2, 5. You can see that the length of the vector, root 29, and therefore A hat will be the vector 2, 5 divided by the square root of 29. Vectors that are parallel to each other, we'll see in the same direction. So vectors are parallel if one can be written as a multiple of another. So if I could say that A is some constant multiplied by B, then the A and B will be parallel vectors. So which of these are parallel? Just take a little bit of time, pause the video if you wish, to decide for yourselves which of these are parallel vectors. Well, hopefully you've seen that the first and the last one here, if we multiply by -2, then we can see that we get 8, -4. So -4, 2 is parallel to 8, -4. The position vector of point is a vector going from the origin to the point. So here we have 2 points P and Q. So we can say that the position vector of P is the vector OP, or we sometimes, or quite often rather, refer to that by its end point. So we talk about that being the vector P. And similarly, the vector from O to Q would be equal to the vector Q. So for this particular diagram, we can see that OP is 4, -3, and OQ, or the position vector of Q, is 3, 2. So we might then say, well, how can we find the vector from P to Q? Well, if we look at our diagram, to go from P to Q, we can start off at P, go to the origin, so that would be the vector from P to O, and then from the origin go to Q, so from O to Q. Now we normally do that. PO is the same as minus OP, so we would say that OQ minus OP is equal to the vector from P to Q. Or putting it another way, PQ is equal to Q vector O minus P. So you can remember that by remembering that it's the right hand one minus the left hand one in terms of the letters. Well, everything we've talked about in 2 dimensions can be done in 3 dimensions. we add in a third unit vector in the z direction, which is k. And normally, if we're trying to represent this on a piece of paper, I and j are sort of drawn as if they were horizontal and k is vertical. And so we just end up with three components, a1, a2 and a3 in the unit vector directions I, j and k. The length of the vector is found in the same way. It's just an extension of Pythagoras' theorem into 3 dimensions, so we get the square root of a1 squared plus a2 squared plus a3 squared. So as an example of that then, we can see here that the modulus of a will be equal to the square root of 2 squared plus 4 squared plus 3 squared, and that gives us the square root of 29. And the modulus of b is equal to the square root of negative 4 squared plus 2 squared plus 1 squared. And that's equal to the square root of 21. We could talk about a unit vector in the direction of these, so a hat would be the vector 2, 4, 3 divided by the square root of 29. So if I write that at the top here, we've got that a hat would be equal to the vector which is 2, 4, 3 and then divided by the square root of its length, so the square root of 29. And also we might want to work out the vector AB. So the vector from A to B, remember, would be vector B minus vector A. So that would be negative 4, 2, 1 for B, and then subtracting 2, 4, 3, giving us a vector negative 6, negative 2 and negative 2. That concludes this video on using vectors, and the next video we'll be looking at the idea of the scalar product of two vectors.